And as you know, Guy is Associate Professor and Samueli Fellow at UCLA in the Computer Science Department, where he directs the Statistical and Relational Artificial Intelligence Lab. And Guy's interests are very wide, and he has made very significant contributions to machine learning, in particular, the statistical relational learning, tractable learning, knowledge representation and reasoning, including graphical models and lifted probabilistic inference and knowledge compilation, and also the applications of probabilistic reasoning and learning and artificial intelligence in general. And Guy has been putting forward the case for techniques of neurosymbolic AI, including probabilistic reasoning, over the last few years in very significant contributions. So thank you so much, Guy, for joining us, and the floor, or the virtual floor, is yours. Thank you so much.
Thank you. Yeah, thanks for inviting me, and I hope you can hear me and see my slides. I guess so. Otherwise, you interrupt me.
Perfect.
Okay, good. So what I wanted to talk about today is this general topic about reasoning about learned models' behavior. And of course, a large part of this type of research I do is neurosymbolic. And I have these general slides to motivate why we should be combining reasoning and learning. But of course, for this audience, everyone already believes in this, but I'll just quickly go through them anyway, right? So traditionally, of course, we have this tension between pure logical reasoning and pure data-driven learning. And one is good at one thing, which is slow thinking, being deliberative, model-based, extrapolate from what we already know, and has some amazing achievements. But of course, logic is often dismissed as being brittle for all the reasons we already know about. And then for a while, maybe 5 years ago, we thought that pure learning was the way out. It's really good at fast thinking, instinctive, perceptive, kind of model-free interpolation of giant amounts of data. And it's done some amazing things. But then maybe in the last 3 years, we kind of came to the realization as a field that also this pure learning approach is brittle, just like logic is brittle. And this is maybe a phrase you don't hear as often because of all of the issues that are here on the slides, right? These are all issues that arise if you just take the data and feed it into a black box model and you get in trouble. And so the reason, of course, is that you fail to incorporate some sensible model of the world, which is, of course, what the good old symbolic AI was excellent at. And so what I do in general, but also for this talk, is finding a nice synthesis between these approaches. Specifically, I'll talk about learning statistical models subject to symbolic knowledge. And I realize a lot of people in this community work on that particular problem, but I hope I can present an interesting take on it. And then I'll also tell you maybe my favorite neurosymbolic technique, which is learning monotonic neural networks. And in all of these cases, we're integrating reasoning, logical and probabilistic reasoning, into the machine learning pipeline, which is another thing that I'm really passionate about. Okay, so the first topic is deep learning with constraints. And of course, many of you have seen versions of this in, for example, vision, where people have to actually hard code into their vision models that Kobe Bryant cannot be in the same frame twice. And of course, if you just train in a purely data-driven way, you won't actually learn this correctly. You see this a lot in robotics, in this estimation problem where you want to figure out what are these objects that are on my camera. If you just train in a data-driven way purely, you will get that these rigid objects end up overlapping, which doesn't make any sense in the real world. And so you want to kind of hard code into your model that this is impossible. You find the same thing in natural language processing, where there's a very rich literature on how to incorporate constraints. And so all of these things kind of motivate us to find a more principled way to do this. And perhaps the biggest motivation we got from this 2016 DeepMind paper, which is a really interesting paper. It was a big deal at the time. It was tweeted about by the CEO of Google. And this paper is trying to train a neural network to navigate the tube in London. It's trying to find essentially the shortest path in a graph. And it's trying to do so using a recurrent neural network. And of course, this is being lauded as a way that neural networks can do logical reasoning. But unfortunately, we know the limitations of pure deep learning. If you look into the supplementary material of the appendix and the fine print, you actually find out that there's something else going on here. What's going on is that the neural network actually learns to send you somewhere where you cannot go. For example, it will tell you if you're currently in LAX, take the metro to Santa Monica, but there is no connection here. So in the graph, it will say, take this edge, but the edge is not in the graph. And so this is an issue, right? The neural network doesn't actually know what the world looks like. It just gives you a rough direction and is very good at giving you that rough direction from data. But you cannot really execute on what it tells you to do. So how do you fix it? Well, in this paper, I mean, these are smart people. They said, okay, we have to fix this. We will actually take the output vector of our neural network and we will essentially cross out all of the things that do not make any sense if you look at the world logically. And we'll just go to whatever is the highest ranked thing we can actually go to. And it gets even worse because then, of course, in the next iteration of this algorithm, the neural network doesn't know how you corrected its predictions. So you have to also tell it what you did to correct its predictions. So this was already, in some sense, a neurosymbolic approach, even though it wasn't really presented as such. So we would like to maybe make this slightly more elegant, right? Because what really happened in the last years with the deep learning revolution is that we still have tons of world knowledge, tons of constraints about the world, but they've kind of gone away. We don't really write our knowledge bases anymore as we did in logical AI. They've gone away and kind of started to hide in Python scripts that cleverly encode and decode, that fix inconsistent beliefs, just like this DeepMind paper. A lot of the autonomous driving systems have a ton of rule-based reasoning going on. There's a lot of data set design, and some of the authors of the examples I showed you before allowed me to call what they did a big hack. And so that's sad, right? We would like to have a more principled and scientific way to actually incorporate this knowledge. Okay, so now I'm really excited to tell you about our latest and greatest approach to this, which is called Pylon. And this is a collaboration with all these wonderful folks here. And our idea was that, yeah, there's a lot of work in neurosymbolic kind of enforcing of constraints on neural networks, but we would really like to make this as accessible as possible. We would like to be really trivial for any kind of machine learning engineer to take their PyTorch existing training setup and just make it slightly better by incorporating constraints. And of course, the setup is the usual one that most of you are familiar with. We have a neural network for structured output prediction. So it predicts a vector of numbers, y. And so what could happen is that these numbers encode some structured object, for example, a path in a graph. And then some of these predictions don't make sense. So this here is a correct path in a graph. This one here doesn't actually correspond to anything, right? Another case could be when the output labels here are just different tasks, for example. It could also be that this is a sequence of words that you want to tag maybe with the entity type, right? So in a lot of machine learning, you have these kind of structured output cases. And usually these outputs are related to each other in some interesting way. And learning how they are related to each other from data is inefficient. And if even DeepMind cannot figure it out with their compute power and their ability to handle large data sets, then it's definitely difficult. And it's much easier to express some of these things declaratively. So in Pylon, what we try to do is to allow people to inject this declarative knowledge super easily. And so this is kind of the overview of the library. You can actually download it today. It's on pip. You can just play with it. There's some demo notebooks. And we just allow users to write arbitrary constraints on the output and write them as just Python code. So just a Python predicate that returns true or false that tells us whether the neural network predicted something that was okay or not okay. And so this means that it requires really a minimal change to your existing PyTorch setup, and everyone should be able to use this. Now, behind the scenes, of course, you have to find a way to take this constraints in Python and somehow optimize it, make it a differentiable loss. And here we support a whole bunch of kind of backend solvers. One of them is the exact semantic loss, which I'll talk about later. We also have Monte Carlo estimates of the loss that are very efficient to compute, T-norm approximations. And so I would invite this community which has even more solvers for this particular task, to also implement your solver in this framework. So we kind of have a one-stop stop for all of the constraints on neural network solvers. So I really hope people in industry will start using this. Why? Because it's really just very easy, right? So you take your existing PyTorch code, which has some loss like cross entropy, which is the data-driven one. You write some function that says check whether the output vector y actually satisfies a logical constraint, and then you return what that is. And here you can, in the most general sense, you can do whatever you want. You can call all sorts of APIs, you can sort your list, you can do any computation you like, as long as you return whether the constraint is satisfied. Then you just add this loss to your existing loss, and you're done, right? So then our solver takes over and turns this into a gradient and does all the work for you, including solving the combinatorial problem of checking whether the constraint is expected to be satisfied. All right, let's look at an example. So this is a really cool example that we saw in this paper here, and we decided to use it because it's really similar to the nature example I showed you, but kind of more fun. So the goal here is to look at this image here, which is a map of Warcraft, and try to find out how you get from the one corner to the other corner. There's a certain cost for traversing different types of terrain, and so this would be the solution, the shortest path to reach one corner from the other. And of course, just like in that nature paper I showed you, the neural network doesn't actually predict anything that makes sense on a whole bunch of these cases. For example, here it says, go over there, and then nothing. And then somehow, if you're here, go over here, right? So the neural network kind of refuses to tell you how to cross this forest here. And what it predicts here is obviously not a path, it's just a collection of edges that somehow gives you good cross entropy, but doesn't actually do the job. Over here, it kind of refuses to tell you how to cross this empty space here. Over here, it doesn't really know how to cross these rocks. And then over here, it's kind of betting on multiple paths simultaneously, hoping that at least one of these will give it a good cross entropy. Over here, it doesn't really know how to cross this water, whether it should land here or here, and you can kind of see what's going on, right? This is what we don't see when we look at our accuracies. We don't see the fact that actually these predictions jointly make no sense at all. If you now plug in the constraint that says, whatever you predict, it should be a path. I don't care which path, but it should be a path, right? You can easily write this function in Python. Then this is what you get, right? So here we see that now the neural network, so mind, we're not really fixing the outputs of the neural network here. We're just teaching it to predict something that actually is a path by enforcing this constraint. So here now you see it does find a way to cross these things it doesn't know how to cross before. Now it does figure out kind of where to cross the rocks, and it kind of chooses a path here that also makes sense. Okay, so this is kind of a cute example, but let's look at the numbers. So here we're trying to predict the paths, and we're reporting 3 types of accuracy. And we call this coherent, incoherent, and constraint accuracy. And the way this works is that, well, let's first see at what is this incoherent loss. So the incoherent loss is kind of the traditional accuracy that we would consider when we're just doing machine learning. It's basically telling us for the individual edges, what percentage of predictions is correct, right? So I kind of average over all the possible edges I could take in the graph, and I ask, do I correctly predict whether this edge is in or out of the graph? So it's kind of separately computing the accuracy on all outputs and then averaging them. And then, of course, this number is amazingly good. Why? Because this is exactly what the neural networks are designed to do very well at optimizing this accuracy, which comes from the basic cross entropy. Now, unfortunately, in only 56% of the cases, what is being predicted is actually a path. And in all of the other cases, you get this kind of random garbage that I showed you on the previous slide. And the real task is what we call the coherent accuracy. This is the real task is predicting the entire path from start to end and nothing else correctly, and it being also the shortest path. And so there you see what's really the gap between when you look at your normal accuracies versus do my predictions jointly make sense, there's just this enormous gap here that is kind of hidden when you only look at this number here. And of course, the goal is to improve this. So let's add this constraint and do this magic of Pylon and have this semantic loss kind of differentiable loss function. And then you see that indeed the accuracy kind of stays the same, right? But this is not what we care about. We end up much more often predicting something that is a path from A to B. And we also much more often end up predicting the correct path from A to B, because now we're actually teaching the neural network to predict the path. I'll tell you later a bit more about this semantic loss effect right now. What is this magic, right? So we've seen a whole bunch of ways of turning logic into differentiable loss functions. So what is this semantic loss? So this is something we developed a few years ago. And the idea is that we want to axiomatize what is the distance between some output vector of probabilities from our neural network to satisfying a constraint in logic called alpha here. And because I'm a knowledge representation person, I really like to axiomatize this. I really hate it when people just say, okay, we want this goal, and now here's a loss function that kind of does something and whatever, right? I really just would like this to be, just following from some basic principles. So that's exactly what we tried. We came up with some basic axioms. You may not like all of them, but a bunch of them do make sense. One of them is saying that if my constraint just says, this is the label and nothing else is possible, then it's kind of like labeling data. So we kind of want to say that this loss here now just becomes identical to cross entropy, right? In some sense, a label is really the same thing as a constraint that just gives you one possible solution. And so in that sense, these should be equal. Another really basic constraint is that if alpha implies beta, then the loss for alpha on the same probability vector should be greater than the loss of beta. So if alpha is more strict, if you put stronger constraints, then the loss should go up or stay the same. It can never go down. Okay, making the logic harder can only increase the loss for satisfying the constraint. There's a few more of these, and they imply some properties. For example, it's pretty obvious from this axiom that if the two constraints are equivalent to each other, then they should have exactly the same loss. So that's why we call it semantic loss, right? So in some sense, this is like the basic thing you want, right? If two people write down the same constraint, then why would the loss function be any different for them? And unfortunately, this property doesn't hold for most of the losses people use in our field. Okay. I'm not going to go into too much detail here, but I just want to give you a little bit of a flavor of kind of the technical details. If you define all of these axioms, you can actually prove that there is a unique loss function that satisfies these axioms. And it looks like this. It's kind of, it's taking minus the log, and then it's summing over all of the satisfying assignments to my constraints, all of the solutions to my constraint. And then this here is computing the probability of that particular solution, as given by the last layer of my neural network, all of the probabilities that it gives me. So this is really the probability of satisfying the constraint alpha after sampling from the neural network's output layer. Now, computing this is sharply hard. So you would never really want to plug in this equation into PyTorch. That would be a disaster. But what we really do is we use logical and probabilistic reasoning tools to efficiently compute this number here. And again, I'm just kind of skipping over some technical details, but just to give some pointers, and then I'll go back to the higher level again. The way this works is we compile our constraint alpha into some logical circuit. And these circuits, they've been developed before in the knowledge representation and reasoning community, and also in the probabilistic inference community for essentially counting solutions to logical constraints. And they look like this. They're logical circuits. And all we really need to do to compute this semantic loss is now turn our ands into products or ors into sums, and for our inputs, plug in the probabilities given by the neural network. So really what this is it's just another bunch of layers on top of my neural network's output layer that computes for me the loss. What's really nice is you can get this computation graph from a SAT solver once at the beginning before you start learning. And then it's very, very fast to evaluate. And it really doesn't slow down your learning at all. Okay, so that's briefly how all of the machinery works behind the scenes, but maybe it's not so important here. Okay, so this was semantic loss, and semantic loss is really good at taking a neural network that predicts things that are non-solutions and then changing it to only predict solutions to our constraint. And so this is visualized here. So Y here is the set of all possible output predictions. The models of alpha are the ones that satisfy the constraint. So these are all the correct paths from A to B. And of course, here we have a whole bunch of probability given to non-solutions to the constraint. Over here, we also have that, but actually the neural network is very certain about a non-solution. So it's very confidently predicting something that doesn't satisfy the constraint. And so in both of these cases, semantic loss will essentially retrain the neural network to give almost zero probability to things that are not solutions to the constraint, and then some probability to everything that is a solution to the constraint. Okay, so this is what semantic loss does, and it's really good at this. But we actually want to do more. We would like to also tell the neural network that it should be very confident about the solution that it predicts. This is in general, in standard machine learning, something that you might call entropy regularization, where you say, I don't care what you predict, but you should be confident in what you predict, because that means that you've actually learned something. And this gives a good signal for training a neural network. And so what we propose in this work, which is currently not yet published, but should be on arXiv next week, we call it neurosymbolic entropy regularization. And so the key idea is that semantic loss can get you here, but it cannot really get you to be confident about any of these predictions that satisfy your constraints. Right? Once the neural network predicts with 100% probability something in this range, it doesn't really prefer anything else. The loss becomes zero, and it doesn't give a signal. At the same time, standard entropy regularization will think that you're doing a great job in this top right corner here, where you've very, very confidently predicted something. The only issue is you've predicted something that doesn't satisfy your constraint. And so in neurosymbolic entropy regularization, what you're saying is that in addition to semantic loss, you need to be very confident about which solution to your constraint you're predicting. I hope this makes sense. Feel free to interrupt with questions, by the way. This is essentially the same slide, but written in math, right? When we have our distribution over our output labels, given our input to our neural network, and a constraint, then semantic loss says that the probability that you satisfy the constraint in your Ys should be very high, and so minus the log probability should be very low. You should minimize this loss over here. And then what I just told you about is neurosymbolic entropy regularization is additionally saying that your entropy should be very low on the space that satisfies the constraints. This is essentially saying minimize the entropy over the solutions to the constraint. So now you might wonder, does this really help me? And the answer is yes, it helps you quite a bit. So just enforcing the constraints got us this 50% accuracy. If you now do the entropy regularization with the constraint, you get another 5% or 4% accuracy on top. In fact, even the incoherent loss increases. So even if you just care about predicting individual edges, suddenly you start to do better. And also you more often predict something that's actually a path from A to B. And you wouldn't get this result for this midline. You wouldn't get the same quality of improvement if you just added entropy to semantic loss. You really want to do this neurosymbolic entropy regularization. I see maybe people raising their hands, or am I not seeing that? I'm not really, feel free to interrupt me if someone has a question, because I don't really see if anyone has.
Okay, I'm gonna make a question, sorry, Guy, by Hector. He said he's confused about figure D, neurosymbolic entropy regularization. Is this losing modalities? Oh, I got the answer in the next slide. It's expectation, the space of solution. I don't know if Hector still has a question, but it's okay.
Yeah, so it's really the distinction between this here, where this could be completely flat. If you could just uniformly predict all possible paths in the graph, then semantic loss will tell you you're doing a great job because you're always predicting something that satisfies the constraint. But in essence, you haven't learned anything because you don't confidently predict something. And the experiments I showed you are for fully supervised learning. So there, even it helps to be confident about which solution you pick. But this is especially important if you have unlabeled data. If you do semi-supervised learning, you get an enormous amount of signal from saying, I don't know what the label is, but you should pick something confidently. And this really gets a lot of signal from unlabeled data. I'm not sure if that answers the question. But yeah, I'm happy to repeat that if it doesn't. Okay, you may wonder, how do we compute this? You know, this looks like a very scary equation here, right? This is an expectation of the log probability. This is an entropy. This is something we're not comfortable actually computing into our loss function. Well, the same machinery that we use to compute semantic loss, where we just took the output layer of our neural network and then made a circuit that computes the semantic loss, in a downward pass on exactly the same circuit, we can actually compute this, this neurosymbolic entropy. And so it's really, again, a very trivial computational task once you've done the symbolic work of generating this particular circuit here. And that's all I'll say about it. I won't bore you with the technical details. Okay, so that was a bunch of techniques for adding constraints on neural networks. The examples I showed you were, of course, kind of toyish examples of finding shortest paths. That's not what maybe someone in industry cares about. But in the Pylon repository, we have a whole bunch of other examples that you might like. A bunch of them are in natural language processing, where these constraints are extremely valuable. It just looks much more boring if I show you this table, right? So here we compare semantic loss with the neurosymbolic entropy regularization to product T-norms, to self-training. We also have comparisons to ILP solvers. And yeah, for these natural language, real-world tasks of joint entity relation extraction, you get enormous boosts in performance from doing this with this neurosymbolic pipeline. All right, so maybe in the next 5 minutes, unless there's more questions about this part, I want to talk about a different topic, which I think is really, really neat. It's much simpler in a sense than what I showed you before, but it's kind of a fresh application of neurosymbolic learning. And that is enforcing monotonicity in neural networks. So here's the setup. We're a bank, and we get a bunch of features from our customers. One of those features is income, and we need to predict how much loan we give to our customers. And so here I fixed all of the other features to some value, and I show you how the predicted loan amount changes with income. And then you should be bothered by the fact that there are cases where all else equals, if someone makes more money, they actually get a lower loan amount approved. And that doesn't make any sense. If you increase the income and everything else stays the same, you know, all other features of this person stay the same, then definitely the loan amount should increase. And you could worry, even when you're at the bank, that if you don't do this correctly, that you might get sued by a customer who's on the bad side of this monotonicity violation. So what we would like is to learn a neural network that is actually monotonic. And sadly, if you just train from data, this will not happen. You will for sure train a neural network that violates this basic monotonicity piece of prior knowledge. And the way that we approach this is using SMT solvers and the notion of counterexamples, which of course are very important in a lot of verification work. So here's a very simple logical constraint that says that if x is less than y, then it must imply that x is the value for x is also less than the value for y. And if it isn't, then this is a monotonicity violation. So this constraint here, if it's true for a particular x and a y, then we call this a counterexample. And so, for example, for a counterexample, this point here and that point here is a pair of counterexamples. These are also a pair of counterexamples, and these are as well. What we care about here is counterexamples that are in some sense the worst counterexample. And so these two counterexamples are the worst violation of monotonicity. And what's really neat is you can find these counterexamples using an SMT solver, a logical reasoning solver, provided that your neural network has ReLU activation functions. This is very easy, very standard. And you can also find these maximal counterexamples, the largest violations, using, for example, an optimization modulo theory solver. So this is some pretty serious logical reasoning here. And what's neat is once we have these counterexamples, we can actually fix in a very interesting way the predictions of the neural network. And fixing the neural network here amounts to computing the monotonic envelope of this function. So what you do is you take every point that you need to make a prediction on, some new customer, and you find its maximal counterexample. In this case, this would be the maximal counterexample. And instead of predicting the value that the function gives you, the neural network gives you, you predict the value of the maximal counterexample. If you do this, you get a guaranteed, for sure, 100% monotonic function, and it looks like this. So this is really neat because you can just do this on the fly. Anytime a new customer comes in, you just take your neural network, find a maximal counterexample, and use that as the prediction. This works not just on these silly two-dimensional examples, it works on high-dimensional input with multiple monotonic features, and you can check the paper for details. So this is neat, right? Now I know for sure that I will never get sued by my customers. There's no way that I can violate this monotonicity at prediction time. You may wonder, how much does this cost me in terms of accuracy? So here we have some regression problems, some classification problems, and the summary is that sometimes the quality of the predictions gets slightly worse, sometimes it gets slightly better. So this seems like you can essentially guarantee monotonicity in this neurosymbolic way at little to no cost. However, we want to do better. We want to actually train the neural network to satisfy monotonicity. We don't want to just fix things in post-processing. The way we do this is we train on normal data, but then every once in a while, we also generate counterexamples.
Sorry, we have to finish in a minute because of the next. Okay,
I'll do that in exactly 1 minute. Okay, so you use these counterexamples and then you say, make them less of a counterexample and add that to your loss function. This is what you get. Monotonicity is a great inductive bias. You just get much better results if you enforce this at training time. And then the real amazing thing is that you can do both. So I can guarantee that the bank won't get sued while also fixing the neural network to be more monotonic. So I can get provable guarantees and state-of-the-art monotonic learning all at once. All right, so that's the end of my talk. I think that was 1 minute. I hope I convinced you knowledge is everywhere in machine learning. You kind of already knew that, and that a little bit of reasoning goes a very long way in actually getting even state-of-the-art results. And I showed you this using deep learning with constraints as a big topic, but also this really nice example of learning monotonic neural networks. And that's it. Thanks for your attention.